We spent the final couple days of last week and yesterday performing a lab on standing waves. You guys know that a standing wave is a wave that appears to be standing still, Nathan, but really in the end is still transmitting energy from one end to the other, is reflecting off of end, interfering, and making it look as if the wave is standing still. Now, depending upon what kind of standing wave we have, what the boundaries are like, the pattern may look a little bit different. If we have a standing wave produced by a string going from one end to the other, then the first standing wave will look like this. The second standing wave will look like this. If we have a wave that maybe is a sound wave in air, and we've got one open end and one closed end, then the first standing wave is going to look like this, where we have a node at one end and an antinode at the other end. The second standing wave is going to look like this. Notice we went from one antinode to two antinodes. If we have maybe just a pipe that we're blowing across the end of, making a sound, okay, then it's going to look something like this, where we have our first standing wave, first harmonic, going to look like this with two antinodes, and our second one is going to look like this with three antinodes and two nodes. Now, the length of all of these is defined as L. We're going to say this is L, this is L, and this is L. What I want to do right now is derive the equation for the first harmonic, not the rest of them, not the second or third or fourth or fifth harmonic. We'll deal with that later on. The first harmonic in each situation. The length of this one, the length of the first one, is 1/2 of lambda. Lambda is therefore equal to 2L. F is therefore equal to V over lambda, which is, since lambda is 2L, we're going to say F is equal to V over 2 times L. That's the equation for the first harmonic of the first situation that we saw, where we have both ends fixed. A guitar string, piano string, right? It's attached at both ends. It's fixed at both ends. Okay, the second situation is where we had an instrument that was open at one end and closed at the other end. Maybe it's a flute. Maybe it's a clarinet. Okay, both ends are different. One end open, one end closed. Okay, in that case, the length of the wave is 1/4 of a wave, 1/4 of lambda. And we're going to rearrange that to solve for lambda. It becomes 4 times L. If F is equal to V over lambda, then F would be equal to V over 4L. So V over 2L when you get two ends that are fixed, V over 4L when you get two ends that are different. Let's go to the third one. This is just blown across the end of the pipe with both ends open. First standing wave that we're going to see, L is equal to 1/2 of a wave. Therefore, lambda is equal to 2L. F is equal to V over lambda, or F is equal to, in this case, V over 2L. Notice that the first one and the third one are exactly the same. When we have two ends that are fixed, like a guitar string, then we've got V over 2L. When you get two ends that are open, like a pipe, then we've got V over 2L once again. Now, I'm not suggesting that if you have a guitar string that's 30 centimeters long, it's going to produce the same fundamental frequency as a pipe that's 30 centimeters long. It's not, because the speed of sound in that medium is different. But the equation that describes the first harmonic will be the same in both cases. The equation that describes the first harmonic when you have one open end and one closed end is going to be different. Here's the rule of thumb. If you get two ends that are the same, it's V over 2L. If you have two ends that are different, it's V over 4L. Does that make sense? Now, I'm suggesting to you that you don't memorize these equations. Okay, you'll probably remember that one of them is V over 2L, one of them is V over 4L, but trying to remember which is which, that's the challenge. Okay, trying to remember which is which. Okay, I have trouble with that all the time still, remembering which is which. I have to figure this out as well, just like I did, remember I told you last week of the whole diffraction thing, the frequency, how diffraction is affected by frequency. I got to figure it out every time, but that's okay. Okay, because that guarantees me that I'm going to be able to figure that out. I'm going to be able to know what it is when I have to. Okay, rather than just trying to remember it and then forgetting it at some point. So, be able to figure that out. But also remember this. There is a second harmonic here that is twice the first harmonic. And there's a third harmonic that's 3 times the first harmonic. And a fourth harmonic, and so on. That's 4 times the first harmonic. Same deal over here. There's a second harmonic. There's a third harmonic that's 3 times the fundamental. And a fourth harmonic that's 4 times the first harmonic. And so on. But the one in the middle, where one end is open and one end is closed. We've got a first harmonic, like we do in the other ones, although albeit a different equation. We also have a third harmonic and a fifth harmonic, and so on. There is no such thing as the even harmonics for one open and one closed end. We call that an open air column. Or sorry, a closed air column. Does that make sense? Now, what's the best way of dealing with the third harmonic or the fifth harmonic or the 17th harmonic? Multiplying the first by 17. You can derive an equation if you want for the 17th harmonic by drawing in all the nodes and antinodes and so on, but we don't need to do that. If we can do it for the first one, then we can figure it out easily for anything above that, as long as we remember that this one doesn't have the even harmonics. It just has the odds. Right? You had some questions over the weekend on this stuff when you had a closed air column where one end was open and one end was closed. It was that second worksheet, and you had questions 1 through 8. Is there any issues with those questions 1 through 8 on that second worksheet? Yep. 5. Any others besides number 5? Is that it? Really? You guys are like this close to being experts on this stuff? There's only one question we need to go over? That's great. Because we're going to have a quiz on this already tomorrow. Perfect. Let's take a look at number 5 then. I'm going to try to make this a little bit bigger so we can see it better. Here's the question. It says, what length of closed air column? So we can have a closed air column which looks like this. We can have an open air column which looks like this. Which length of closed air column produces a fundamental frequency? What's another word for fundamental frequency? 2 words. Yep. The first harmonic. It produces a fundamental frequency, first harmonic, at 256 hertz at 20 degrees Celsius. Well, let's deal with that 20 degrees Celsius first. You guys know how to deal with that, right? In the context of sound, whenever you see a temperature, let's get the speed of sound. Always, always. Just automatically, blindly. If you've got the temperature, find the speed of sound. If it's in air, that is. We're going to say V is equal to 331 plus 0.6 times the temperature. So it's going to be 331 plus 0.6 times 20, which gives me, I believe, 343 meters per second. Good. There's the speed. We've got a fundamental frequency of 256. Let's derive the equation for the fundamental frequency here. Here's my air column that's closed, open at one end, closed at the other. Here's the first harmonic that will be produced. The length of this is 1/4 lambda. Lambda is equal to 4L. We're going to say F is equal to V over lambda, or F is equal to V over 4L. We're solving for the length here. So let's rearrange that. It becomes L is equal to V over 4 times F. The speed we just calculated is 343. The frequency is 256. So make sure you multiply that by 4. Do the math there. We're going to get somewhere around 0.32, 0.33. The 3 digits, it should be 0.335 meters. Is that okay? Okay, what if they had to change this question just a little bit? Okay, they didn't, so nobody's got this part done. That's okay. What if they had to change it to say, what length of closed air column that produces a third harmonic of 256? What if they had said a third harmonic of 256? What would you have done there? Okay, it changes the question, right? So what we see down below here that we've already answered is now wrong. Okay, that was based on that being the first harmonic of the fundamental. There's 2 ways we could change our solution to make this correct, if that's the third harmonic. What's one way? Yep. You know what, let's tackle it from the beginning, and then we'll get to that and see if you're right there, okay? One way that we could tackle this is to say, look, the third harmonic is 256. What's the first harmonic? 256 divided by 3, right? So in that case, F1 would be, the first harmonic would be 85.3 hertz. If we've got the first harmonic, we could go back and do exactly what we just did here, except instead of plugging in 254, we would plug in 85.3 hertz, right? And what effect is that going to have on the length? If the frequency is lower, 3 times lower, then the length is going to be 3 times bigger, right? So you're right. We just want to go at it from a fundamental aspect there. The other thing we could do here is instead of taking the third harmonic and dividing it by 3 to get the first harmonic, we could just stick with the third harmonic and derive the equation for the first harmonic like we did. But then, what would we do? Change the equation, right? Instead of being F is equal to V over 4L, which is the equation for the first harmonic, for the third harmonic, we'd say it's 3V over 4L. We could still use the frequency that was given to us at 256. Okay, use V, solve for L, and lo and behold, it would be what we would get the other way as well. So get the first harmonic, use the first harmonic equation, or get the first harmonic equation, change it to a third harmonic equation, and then do your thing there. Does that make sense? Okay. You guys feel okay with that? If I was hypothetically to give you a quiz on this tomorrow, do you think you'd be okay? Yeah? Here's one for you. Couldn't give you this because it's not completely unlike a question that you're going to see on a test, but you got a bottle of Coke here. It's 24 centimeters long. It's half full of Coke. Half full. The temperature of the air is 20 degrees Celsius. I want to know the sound that you hear when you blow across the top of this pop bottle. Yeah, I blow across the top of my water bottle. What sound do I hear? What's the pitch of the sound that I hear? Which one are you predominantly going to hear? First harmonic, second harmonic, third harmonic? First harmonic, right? Which one do you know for sure you're not going to hear? Second harmonic, right? Because there is no even harmonics there. So if you hear anything, it's going to be the first or the third. We're going to solve for the first harmonic here. Okay, we're going to say that we draw this out. Okay, we're going to say that the length of this is 1/4 lambda, or lambda is equal to 4 times L. We're going to say that F is equal to V over 4 times L. V over lambda, which is 4 times L, right? So F is equal to V over 4 times L. Let's figure out what the frequency is here now. V is going to be 331 plus 0.6 times 20, which gives me 343. And we divide that by 4 times the length. What is that going to be? 0.24? 0.12, right? We want the length of the air column. It's not 24 centimeters. Okay, that's a bit of a trick. The length of the air column is 12 centimeters. The sound reflects off of the boundary between the air and the pop, right? So 343 divided by 0.48 gives me somewhere around, it's going to be 680-ish, 685, somewhere around that value. Oops, let's change that. 714.6. We'll go 715 then. Thank you, guys. What's the next harmonic that would be produced? How would you find it? What's the easiest way to find it? You derive the equation for the next harmonic, or you could simply take this value, 715 hertz, and do what with it? Multiply it by 3. Good. Multiply it by 3, not multiply it by 2, because there is no even harmonics here. If it was a guitar, you'd multiply it by 2. If it's an air comb, you multiply it by 3.